In this lecture, we are going to look at Chapter 1 of Dixit, which is why I've entitled this as Introduction. So we begin with a standard budget line. All right, the budget line is given by this line here, and it is also given by this equation. All right, this equation here, where we have P1 is the price of good one, Q1 it refers to good Q1, and P2 is the price of good 2, and this M is our budget, or sometimes it's referred to as income, which we'll discuss below. The utility function is given as a function of Q1 and Q2, and it is drawn in this particular Q1, Q2 graph by a number of indifference curves, and we show 3 here, where U1, U2, and U3 refer to the number of utility units that we would get in any one of these indifference curves. So U3 would represent a higher number of utility units than U2, and U2 would represent a higher level of utility, or a higher level of utility than U1. So in other words, as we increase in this direction, we increase our happiness, so to speak. All right, now the optimum choice, of course, occurs where there's this tangency point, and we're going to talk about that a little bit as we go along. Now, the other thing to note here is that if our entire budget is spent on Q2, then this is the amount of Q2 we would be able to purchase, and this point here would represent the intercept on the vertical axis of that budget line. Likewise, M over Q2 is the maximum, M over Q1 is the maximum amount of Q1 that could be purchased, and this then represents the point on the horizontal axis where the budget line intersects. Now, for each indifference curve, of course, there's a constant. So for indifference curve U2, that constant would be given by whatever number is represented by U2, and these are basically constants. The budget line, as I've mentioned, is given by P1 Q1 plus P2 Q2, where M is the budget or sometimes income. And suppose we randomly give a person in question, a person who's represented by this particular system of indifference curves, let's suppose they start here at this blue point, all right? And we ask the question, can they do better? Well, obviously they can, because their number of utility units lies somewhere between the amount U1 and U2, and they would do a lot better by moving in the direction of the black dot, so from the blue dot towards the black dot. How do they do that? Through something called arbitrage. All right, so the person can reach a higher level of utility or satisfaction by giving up some small amount of Q2 for more Q1. So in other words, they would give up some Q2, they'd go down in this direction, giving up some amount of Q2, and then they would end up right here. So they would give up that much Q2, and in exchange, they would then purchase that amount of Q1. Now, how do we know how much they have to give up of Q2 and how much Q1 they would get? Well, we'd have to look at first off, the number of units, number of physical units they would have to give up is given by the amount of Q1 they want to buy, and the amount of Q1 is given by some change in income divided by P1, and the amount of Q2 that they have to give up is given by the change in income, which we denote DM, divided by P2. So DM refers to a very small amount as we move along that budget line. So the utility of more Q1, so if you're going to get more Q1, is given by the marginal utility of 1, all right, multiplied by the amount of Q1, the change in Q1, that you'd get from this little bit of a change in M as you move income from the purchase of 2 toward the purchase of 1. So from the purchase of 2 to the purchase of 1, that's how much Q1 you'd get. So this is equal to this dQ1. And you'd have less Q2, and the utility of less Q2 is then given by the marginal utility of 2 multiplied by this dQ2, which is simply equal to dm over P2. So the overall change in utility is then given by the marginal utility of 1 times the amount of Q1 that you've purchased plus the marginal utility of 2 times the amount of good 2 that you give up. All right, and actually this would be a negative amount because you're giving it up. So the arbitrage condition is given by this exchange. And we know that, as I've already mentioned, that dQ1 is given by dm over P1. It has to be positive, whereas dQ2 is equal to dm over P2, and it has to be negative because you're giving up Q2. So this amount here would be negative. This would be positive. Both the marginal utility of 1 and the marginal utility of 2 are assumed to be positive. You can't have negative marginal utility. That is a decline in marginal utility. All right, so we assume that the utility function itself is positive. So in other words, if we have U, Q1, Q2, all right, then du, dQ1 is the marginal utility of 1, and it has to be positive. And I just put an I here where I is 1 or 2. And the second derivative of the utility function with respect to any given Qi is negative. So this one is positive, this one is greater than 0, this one is, the second derivative is less than 0. So what we're saying here is that this utility function is continuously differentiable in Q1 and Q2. All right, and of course we don't have a negative marginal utility because of this right here. Okay, now it turns out that the marginal utility of 1 times the dQ1 minus the marginal utility of 2 times the change in Q2 is given by this amount here, mu1 over P1 minus mu2 over P2 times the change in the income. So arbitrage turns out to be beneficial if the marginal utility of 1 divided by the price of 1 minus the marginal utility of 2 divided by the price of 2, all multiplied by the slight change in income, is positive. But because the change in income is non-zero, we can get rid of it. So as a result, this is our arbitrage condition. If it's greater than 0, then it is worth undertaking. In other words, the movement from the blue to the black point in the above diagram is worth undertaking. It's not worth undertaking, however, if this is negative. All right. In other words, the benefit of increasing Q1, so we're increasing Q1, we're decreasing Q2, but if the benefit of increasing Q1 is less than the benefit measured in utility units of reducing Q2, then it's not worth undertaking. So in that case, arbitrage in the opposite direction may be preferred. So in other words, instead of giving up Q2 to get Q1, we give up Q1 in order to get more of Q2. All right. So in equilibrium then, arbitrage is no longer possible when the marginal utility of 1 divided by the price of 1 is equal to the marginal utility of 2 divided by the price of 2. And we call this the tangency condition, as you'll note in your textbook. Now let's rewrite that budget constraint, all right, this original budget constraint, in terms of Q2. So we're going to solve the budget constraint for Q2, which then gives us Q2 equals the budget M over P2 minus P1 over P2 times Q1. And this part here is the intercept of the budget line. Remember, if we go back to the top here, this is the intercept of the budget line. And the slope of that budget line is given by this value here. All right, and it's negative, so it's negative P1 over P2 times Q1, and P1 over P2 negative is the slope. We can rewrite the tangency condition as marginal utility of 1 over marginal utility of 2 is equal to the price of 1 over the price of 2. So in other words, what we're doing is we're just rewriting this tangency condition to get this tangency condition here. Now, consider an indifference curve. The slope of the indifference curve is simply the marginal rate of substitution in consumption, and we denote that with the acronym MRS. All right, it does not refer to misses, it refers to the marginal rate of substitution. If a marginal loss of dQ1 units of Q1 is just compensated for by a gain of dQ2 units of Q2, then the marginal rate of substitution is given by MRS equals dQ2 over dQ1. All right, now the interesting thing to note is that dQ2 over dQ1, it turns out, and we'll see that in later lectures, that is also the slope of the indifference curve, okay? But we'll get to that in a later lecture. In utility units, the exact offset of the gain, that is the gain of dQ2 units of Q2 by marginal utility of 1 times the change in Q1 is equal to the marginal utility of 2 times the change in Q2. So then the marginal rate of substitution, which is given by dQ2 over dQ1, is also equal to the marginal utility of 1 over the marginal utility of 2. At the tangency point of the slope of the indifference curve is equal to the slope of the budget line. So this is important because at the tangency point we know that the slope of the indifference curve has to equal the slope of the budget line. So given that the slope of the indifference curve is simply the marginal utility of 1 over marginal utility of 2, so the ratio of the marginal utilities, okay, that's given here. That's how we get that. And that has to equal to the slope of the budget line, which is simply the price of 1 over the price of 2. Okay, but it has to be, in both cases, there's a negative in front and they cancel out. Now, there's a possibility of getting a corner solution, all right, given by this little blue line, or this blue dot rather, where you don't get a condition of equality. In other words, this condition does not hold. And the reason for that is that it's a corner solution. Now, it can hold, but it doesn't necessarily have to hold. So we can get a corner solution if the marginal utility of 1 over the price of 1 minus the marginal utility of 2 over the price of 2 is less than 0. All right, so this is the condition that results in, this is the condition that comes about when you're at that particular corner solution. And we'll talk about corner solutions a bit later on in the course as well, because those are important and they have to be examined through what we call the Kuhn-Tucker conditions. All right, let's look at the marginal utility of income, which is a different concept than the marginal utility of good 1 or good 2. So let's return to our equilibrium where both goods are bought. So that was the black point in our initial figure. And suppose that income increases by some small amount given by dm. Now this income could be spent to buy only good 1, in which case we would have the ability to buy this change of income over P1. That's how much Q1 we can buy. Or we could buy dm over dm over P2 amount of Q2. So we can either spend it on Q1 or on Q2, or we can buy both Q1 and Q2. And again, we're going through this arbitrage condition. So the utility units associated with these choices are the marginal utility of 1 times the change in M over P1 for good Q1. So this is the amount of utility units we get if we just simply buy all Q1 with our change in income. Or we can buy this amount of utility units, all right, given by MU2 times the change in income over P2. So this is the change in Q2 for Q2. So the utility increment per unit of additional income, and actually it's not income, and that's sometimes confusing as well, but it's rather the per unit increment of additional budget. All right, sometimes we confuse that, and your textbook does the same, and I'll do that the same throughout, because we refer to this marginal utility of income using this notation lambda. So lambda is referred to as the marginal utility of income. But lambda plays another role here because we're going to be using it once we talk about the Lagrangian. Then lambda is referred to as the Lagrangian, and in certain circumstances it is the marginal utility of income. All right, so this lambda will play an important role when we get to Lagrangians. But for now, we find that this lambda is equal to the marginal utility of 1 divided by P1, and it's equal to marginal utility of P2. So in equilibrium, these two have to equal each other. Marginal utility of 1 over P1 equals the marginal utility of 2 over P2, which is assured by this arbitrage condition, by doing the arbitrage that we had before. Now, suppose that we have n goods, and these n goods have prices P1, P2, ... Pn, and quantities Q1, Q2, ... Qn. Then we find that the marginal utility of any good I divided by the price of I, so up here again, all right, is equal to lambda if xi, and that should be a qi. Let me just change that a minute. This should be a qi, 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 qi. So then the marginal utility of I over pi is equal to lambda if qi is positive, is greater than 0, and it's less than or equal to lambda if qi is equal to 0. And we can rewrite these two conditions as follows. All right, MUI minus lambda pi, and we'll see later why we would want to write it this way, is equal to 0 if qi is greater than 0, and this expression is less than or equal to 0 if qi is 0. All right, now this lambda plays a very important role, as we'll see later on, and that role pertains to the use of Lagrangians, which is a mathematical technique that we'll look at for solving constrained optimization problems. Now, the reason I use QI, and your textbook uses XI, which is why I wrote it the way I did, I use QI to represent final goods. So these are the final goods that consumers consume, and I use XI to represent inputs. All right, so I'll try to be consistent in that throughout the course, using QI to represent the final goods and XI to represent inputs. Now, let's consider the case of non-binding constraints, which is the last topic in Chapter 1. And let's assume that we have a quadratic utility function that looks like this. U, Q1, Q2, so it's a function of Q1 and Q2. Alpha is gamma is the intercept term. A1, Q1 minus B1, Q1 squared, and so on. And you notice that this is a quadratic utility function. Now, if I take the first derivative and set it equal to 0, all right, this is what you learned in Math 208. You can set derivatives equal to 0 to find maximum points. We find that the maximum Q1 is given by A1 minus C Q2 over 2B1. All right, and if there's no interaction between Q1 and Q2, so if C were equal to 0, then this would drop out, and we just have A1 over 2B1. The same thing with Q2, taking the first derivative, the partial derivative, and setting it equal to 0 gives us Q2 star, and this is the result here. And the point being that you get a satiation point right here. So in other words, if you try to increase Q1 beyond this Q1S, where S refers to satiation, your marginal utility turns negative. All right. In other words, there's a reduction in marginal utility, So if you try to increase beyond the satiation point, either in this direction, which I've marked, or increasing Q2, you end up with a lower level of utility or lower number of utility units. Okay, given the possibility of satiation, and assuming that saving is not a good, so we're abstracting here from savings, we should write the budget constraint as an inequality rather than an equality. Yet in most of economic theory, we talk about these equality constraints. So we can think of a slack good, a slack variable, if you like, that absorbs income when satiation occurs. All right, and let's denote that slack variable by Q3, that slack good. So what we're doing is, instead of forcing, which the equality sign would do, so if we had enough budget, if our budget line happened to lie, let's say out here somewhere, okay, if this was our budget line, then we would end up at a point where the utility function would touch right here, but we've gone down in utility from the black point. So at the blue point, we have less utility than at the black point in the middle there. So we don't want to have that happen to us. So in order to do that, we need this inequality sign, and to do that, we need to add this Q3, which is a slack variable which would absorb any income that would be higher than needed to reach the satiation point. Okay, now I'm going to end by noting that this Q3, this slack variable, has meaning, and it's a very important one when we're going to look at some linear programming a bit later in the course. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.